Hi, so for today we are going to talk about an application of differential equations, first order, about the problems on orifice problems. So basically, when we say orifice problem, we have a tank or a cylinder that has a small hole on its part of the cylinder. Okay, just as like as in this image. So we have here a cylinder which is filled with water, and it has an orifice, a small opening on the bottom of its cylinder. So basically, we are going to find the problems involving the orifice involves we are going to find the height of the water at a certain time, or the time it takes for the water to actually completely drain the cylinder. Okay? So we have here the differential equation whenever we are trying to calculate, okay, problems in orifice. So we have the change in volume dV all over dt, and we have equals negative a square root of 2gh. So again, dV all over dt is the rate of change of volume. Okay, that is equal to the A, where A is the area of the orifice. Okay, it's a small opening. And G is the acceleration due to gravity. So we can use 32 feet per second squared if it is in English unit. But in SI, we can use 9.8 meters per second squared. And H is the height of the water or the liquid inside the cylinder. So let's try to actually answer a simple problem involving the orifice. So for the problem number 1, find the time required for a cylindrical tank of radius 8 feet and a height of 10 feet to empty the water. Okay, so we have to empty the water through a round hole of radius 1 inch. So it has an area of the orifice here as the uh, radius having 1 inch. Okay, so assuming that the cylindrical tank is initially full, use G equals 32 feet per second squared. So let's try to list the given. So we are actually given a radius of the cylinder 8 feet. Okay. And then we have a height of the cylinder which is 10 feet. Okay. And then we have a round hole. Okay. That's the radius. This 1 inch is the radius of the orifice. So we can denote it as R sub 0, R naught. This is the radius of the orifice, and that is equivalent to 1 inch. So as you can see, we need to be consistent with the units. So if this is 1 inch, we want to convert this into feet. So if this is 1 inch, I'm converting it into feet to avoid um, inconsistency in the units. So 1 inch equals 12, okay, 1 feet. For every 1 feet, there is a 12 inch. So this would cancel. So we have 1 all over 12 feet. Okay, that's the radius of the orifice in terms of feet. Now we are going to use G as 32 feet per second squared. Okay, so let's go now to our solution. So for our solution, we're going to use the formula dV all over dt equals, we have negative a square root of 2gh. So how are we going to do that? So we need first to get the volume of the cylinder. The volume of the cylinder is actually pi r squared h. And since we have a differential of volume with respect to time here in our equation, left side member of the equation of our equation, so we're going to differentiate this volume of the cylinder with respect to time. So as you can see here, we have dV all over dt. So we can actually what? This is a constant, pi, and we can apply product rule with r squared and multiplied by h. So if I apply product rule, I can copy r squared and differentiate h with respect to time. Okay? And plus, I can copy the h, okay? And I'm going to differentiate r squared with respect to time. Oh, so r squared, okay? So that would be 2r, and then I have dr all over dt here because I get the derivative of r with respect to t. Okay? So I have now pi, we have r squared dh all over dt plus I have 2hr dr of dt. So, but take note, class, take note that the radius of the cylinder does not change. Okay? So, the radius of the cylinder here, r squared dh all over dt, and I mean this dr all over dt, okay, here, does not change. The radius does not change of the cylinder. Okay? It's constant all throughout the process. Again, so dr all over dt is 0 because the radius of the cylinder does not change. Okay, cylinder does not change. So if that does not change, there is no change in dr. So technically, this term, 2hr multiplied by dr all over dt, where dr over dt equals 0, technically that would become pi. Then we have r squared dh all over dt plus 2hr multiplied by 0. So technically this would be 0. So you are left with dv all over dt as equal to pi r squared dh all over dt. Where r here is the radius of the cylinder. So we can technically replace this r with 8. So we have 8 pi 8 squared. We have dh all over dt. Okay, so in other words, I have 64 pi dh all over dt. So that is my dv all over dt. Now, it's time to find, okay, it's now time to find what is the, from our formula, area of the orifice and then multiplied by the square root of 2gh. So here we have our dv all over dt as 64 pi again, dr all over dt. So I'm going to equate this in our equation here. So I have 64 pi dr all over, dh all over dt, I mean. So that should be dh all over dt, I'm sorry. So this would be dh all over dt. Okay. So let me just replace this again. So you have dh all over dt equals the area of the orifice. That's the definition of our A. So if the orifice has a radius of 112 feet, so that's a circle, the surface area or the area of the circle is pi r squared. So still we have negative pi, okay? And then I have squared 1 all over 12 squared. Okay, that is in terms of feet. Okay, so that's the area of the circle. That's the area of the orifice multiplied by the square root of the 2 multiplied by the acceleration due to gravity, 32. And the h, that's the height of the water. That we don't know. Okay, so we have 64 pi dh all over dt. So we have negative pi all over 144. Okay? And we have square root of 64h here. Okay? So I have square root of 64h here. So what can I do is actually what? 64 pi dh all over dt. So I have negative. I can factor out. So since this is 64, the square root of 64 is 8. So it becomes negative 8 all over 144 square root of h. Of course, not forgetting the pi here because we also have pi here. As we all know, we can cancel the pi. Okay? Oops. We can cancel the pi there because once we divide both sides by pi, it would be actually canceled. Let me just rewrite this or try to change my pen. Okay? So if I'm going to simplify still, 64 dh all over dt negative 8 all over 144 square root of h. Okay? So what will happen is that dh all over dt, if I'm going to divide both sides by 64, this would happen. Negative 8 all over 64 times 144 square root of h. Okay? So if we are going to simplify this term, okay, this term, so this would be dh all over dt equals, so this would become 1 and this would become 8. So 8 times 144, that becomes negative 1 all over 1152 in the denominator multiplied by square root of h. And hence, we have a variable separable if we are going to manipulate this equation. So we have dh all over square root of h equals negative 1 all over 1152 dt. So if we integrate both sides of the equation, so what are we going to get is that we have this dh, so we have integrate the h raised to negative 1 half. Negative because I used the exponent rule. I converted this into 1 half, h raised to 1 half, and get the reciprocal. Thereby, I have to negate its exponent. So we have dh, and then I can factor out in this integral the constant. Okay, thereby leaving only dt inside the integral because that's the property of integrals. Okay? So upon integrating this, this would be h raised to 1 half all over 1 half. Okay? And then I have now equals negative 1 all over 1152 integral of t, that's t. Then we have plus c as our constant. So simplifying this, so this becomes 2 square root of h. Okay? Then we have negative 1 all over 1152. This is only, you get the reciprocal of the denominator and then multiply by the numerator. That's the rule. Then t plus c. Okay? So this would be our equation. Okay? We can find what we are trying to find, okay, is the assuming that the cylindrical tank is initially full. So, what are we going to do is that we're going to find the value of C. At time equals 0, okay, the tank is full. Okay, the tank is full. Of course, the time that actually equal to 0 is the tank is full because the time has not yet started for the orifice to drain the water. So we have the height. Okay, what is the height of the cylinder? The problem says that it is full. So that we assume that the height of the water during time equals 0 is also the height of the cylinder, which is 10 feet. Okay, so we need to substitute the values. The height is 10 feet. So again, if we're going to solve that, so we have 2 square root of 10, okay, equals negative 1 all over 1152 multiplied by the time, which is 0, plus c. So hence, it's very clear that the value of c here is 2 square root of 10. And now we can substitute this value of c to have a particular solution. So we have 2 square root of h equals negative 1 all over 1152, okay, plus 2 square root of 10. Okay, and that is our particular equation or the model equation. Now, the problem is asking us what? Okay, the problem is asking us, what do you call it? Find the time required for a cylindrical tank of radius to empty the water. Okay? So meaning if we are going to empty the water here, okay, we have time here. If we are going to empty the water, it means that the height of this h, okay, would be 0. Okay? That should be 0. So 2 square root of 0, this is 0. And then we're going to get the time. Isolate the time. Okay? So that we have to get the time. So, I'm going to transpose this. This becomes 1 all over 1152. T equals 2 square root of 10. And of course, if I'm going to isolate t, so I have t equals 1152 multiplied by the 2 square root of 10. Okay? So what is the unit of time that we're going to get here? Since we use 32 feet per second and all of the units are in terms of feet, then definitely this time that we will get here is in terms of seconds, and that is 7285, okay, 0.89 seconds. So that is the amount of time that it will take for that cylinder to drain its water having an orifice of that radius 1 inch. Okay? So to get the model equation at any time at height t, just simply get here in terms of h. Isolate h here. Okay? So that the left side of the equation is in terms of h. And you can now find the height of the water at any time given t. Okay? So that's how simple it is. Okay? So converting this, we can also convert this into seconds or minutes, I mean. So you have 7285.89 seconds multiplied by 60 seconds here because 1 minute equals 60 seconds. So 60 seconds will be cancelled. So basically, we are dividing only this into 60. So if we divide that, that would be 121.43 minutes. That's approximately 2 hours. Okay. So that's the answer for number 1. So let's try to go now for number 2. A jacuzzi full of water is being drained by its sink due to gravity, not by a pump. So that's an orifice. How long before all the 10 cubic meters of water, okay, we're going to remove 10 cubic meters of water is drained? If the dimensions of the jacuzzi is 3 meters in its size and the area of the orifice is 0.1 meters squared. So let's try. Okay. So we are going to assume that this jacuzzi is a cube. So the volume of cube equals length times width times height. Okay? So the one characteristic of cube is that they have the same length, width, and height. So basically, that would be 3 meters multiplied by 3 meters multiplied by 3 meters. So that would be 27 uh, cubic meter. Okay, that's the volume of the cube, okay, of the jacuzzi. So we also have a given of the area of the orifice, okay? Area of the orifice, A sub O, that's 0.1 meters squared. And since we are using in terms of meters, we can use 9.8 meter per second squared as our G. So as for our formula, we have dV all over dt, negative A square root of 2GH. So again, we are going to differentiate V with respect to T because we have length, width, and height. So product rule comes in for this differentiation. So I'm going to copy first the L and W, and then I'm going to differentiate H with respect to T. And then the same thing, add. I'm going to copy L and H and differentiate W with respect to T. And plus, last but not the least, I'm going to copy W and H and differentiate L. So I have dL all over dt. So that's product rule. That is product rule. Okay? That is the review of differential equation. Differential calculus. Okay. So, since the width, okay, and the length, okay, does not change because our concern here is the height. That's the height that changes, okay? That is the volume, okay? Because that's the height that changes because it's going down, okay? So the width and the length have no concern with the water that is being drained in the sink. So our movement of the draining of water is from up to down. So the height changes, okay, except for the width and the length. So if the width and the length does not change, then it should equal to 0. So then we have an equation that this is 0 because it's multiplied by 0, and this is again 0. Okay? So our equation for dv all over dt is only length times width and differential in height multiplied by with respect to t. So length is 3 and width is 3, dh all over dt. So hence we have 9 dh all over dt as our dv all over dt. Okay? So now that we get the dv all over dt, now we are ready to substitute it. 9 dh all over dt equals the negative of the area of the orifice from our formula. That's 0.1 multiplied by what? Twice the 9.8 acceleration due to gravity, and of course the height. Okay? So that's the unknown. That's the changing because we have dh all over dt here. Okay? So what are we going to do is, again, we have dh all over dt equals, we have negative 0.1 square root of 19.6 h all over 9. Okay? And we're going to use the property of the radicals in this equation, okay, to actually isolate h. So we can rewrite square root of 19.6h as square root of 19.6, okay, multiplied by the square root of h. So I can factor out square root of h outside of that. So we have dh all over dt equals negative 0.1. And I have square root of 19.6 here multiplied by the square root of h here all over 9. Okay? So that I can separate the variables. Divide both sides by square root of h and multiply this dt onto the other side. So we have dh all over the square root of h equals, we have negative 0.1 square root of 19.6 all over 9 multiplied by t. And hence, we have arrived to a differential equation solvable again by what? By variable separable. So if I'm going to integrate both sides, okay, so what will happen is that, as usual, I have h here raised to negative 1/2, just like the same formula a while ago, and I can factor out the constant here outside of the integral so that I can freely evaluate the integral of t. So we have integral of t. I have dt here, of course, dt. Okay? So we don't have t here. I'm sorry. This is dt. Okay? Because we have transpose or we have cross multiplied. So this is technically dt. Let me just rewrite it with red so that it's consistent. So this is dt. So also this is dt. Okay, the integral of dt. So it's very easy. Again, we have seen it a while ago on how we are going to do integrate this. This is power rule. So this is 2 square root of h when simplified. And then negative 0.1 square root of 19.6 all over 9 t plus c. Okay. And then, of course, we need to find the value of c. Okay. We need to find the value of c. So now, at its initial state, meaning time equals 0 when the water is about to drain, 0, okay, the height of the water is equivalent to the height of the cube, okay, which is 3 meters. So I can substitute h as 3 meters here in our equation. That should be 2 square root of 3. And then substitute t equals 0. So to find the value of c. Okay? So our t would be 0. So this term would be 0 plus c. So hence, our value of c is 2 square root of 3. Okay? And then we have now the particular solution. So such that we have 2 square root of h equals negative 0.1 square root of 19.6 all over 9 t plus 2 square root of 3. Okay, that is our model equation. So the question is asking us, the problem is asking us, okay, how long before all the 10 cubic meters of water is drained? So the question is actually asking us how long, okay, the time it takes for the 10 cubic meters of water is drained. Okay, so to know that, we know, class, that the volume of cube that we have gotten a while ago is actually 27 cubic meter. So if we are going to remove 10 cubic meter, we're going to minus it to the volume of the cube. So we have 17 cubic meter if we remove 10 cubic meters of water. Okay? And we are now going to get the height, okay, of the water, okay, during its 10 cubic meter is removed from the pool. So we are going to use again the formula L, width, and height. So we know that the volume should be 17 cubic meter remaining on that pool when we remove 10 cubic meter. So the length is actually 3. It's not changing. And the width is actually 3. But the height of the water, okay, in that jacuzzi, that's the unknown. During 17 cubic meters. Again, why 17? Because we removed 10 cubic meters. Because that is what the problem is asking. So, now, our height would be simply 17, okay, all over 9 meters. So, why did we get that? Okay? Why did we get that? So that we can substitute this height when 10 cubic meters is removed from the pool into our equation to get the time it takes for that to happen. So, now, if we are going to substitute it, okay, substituting the height, okay, we know that the volume of this height is 17 cubic meters. 10 cubic meters was released. Okay? So, now, we are going to substitute it. Okay? Substituting it in our equation. So, we have 2. And then, we know that that should be square root of 17 all over 9. Okay? And that is equal to negative 0.1 square root of 19.6 all over 9t plus 2 square root of 3. Okay? And then what I'm going to do is I'm going to multiply 9 both sides of the equation so that this 9 would be cancelled. So that would be 9 times 2 square root of 17 all over 9. Okay, and I have here negative 0.1 square root of 19.6t plus this would be also multiplied by 9. Okay, square root of 3. So now I can easily isolate the t, okay, to get t. So I can what? I can have 18 here multiplied by the square root of 17 all over 9. I can transpose this also on the left side. So this becomes minus 18 square root of 3. And I can divide it by negative 0.1 square root of 19.6. And that is the time it takes when 10 cubic meters is removed from the jacuzzi. Okay? So, that time that we are going to solve there is actually what? In terms, again, of seconds. So, that is actually in terms of seconds. So, if we solve that, that would be 14.54 seconds. And that's it. I hope you learned something for today's video about the Orifice, the application of one of the applications of differential equations. Thank you so much for listening. If you're new to my channel, kindly subscribe and let me know your thoughts about this video. Thank you so much for listening. Again, please don't forget to subscribe. This is Engineer Abat. See you again on the next video.